quick. So this problem's on there. So try this practice problem, please. Then someone make sure I resume the recording. Thank you. Thought I was. Okay, 2.502. Is everyone okay with this so far? Is everyone talking, driving me nuts? Yep. Yep. Pretty predictable. Okay, did it say how much water there was at the start? Nope. So we assume it's 0. I'm going to put a plus sign right here, a minus sign right here, and a minus sign right there. You don't have to do that. You can do them later, but I'm going to do it so I don't screw up. Okay, at equilibrium, it says there's 0.85 hydrogen, correct? Everyone okay with that? Okay. What's the difference? What? 2.4? Okay, what would this difference be? Negative 1.2, because the difference is 1/2 of what this was. What's this difference? 2.4, because it'd be 2 over 2 or the same. All right, so now I just apply math. 1.3, 2.4. Then we're ready to plug it in. These are long, which is sort of annoying. Let me just, come on, Tom. You're better than this. All right, so now we'll just plug it into the expression. The product was H2O and there was 2. So it's 2.4 squared over 0.85, and that was for hydrogen, so that was squared as well. 1.3 was for O2, which was not squared, so it's just that. Or it didn't have a coefficient, so it's just this. All right, when you plug this in, what do we get? 6.13. Who agrees? Sweet. I feel okay about that. Not awful, right? Okay, 6.13 it is. All right, so what is, oh, so that's right here. If the vessel was at room temperature, whatever, what would Kp be? So you'll get 2 answers here, I guess. So Kp equals what? Kc times RT. Good. I know looked all that except for the Kc. I'm pretty proud of myself. So I'm going to put 6.13 times 0.0821 times 298. All right, if you treat them all as gases, you end up with 2 minus 3, right? And so it's to the -1. And who typed that in and is confident in their answer? 0.25. Okay, 2 people have that. Who has that answer? Raise your hands. Okay. If you treated it as whatever, you got 0 minus 3, right? So this is a -3. And what would that have been? Did anyone do that one? That with the Corbin, you didn't do it? What was your answer? Oh, I got 2.5. Oh, interesting. Okay, good enough. Who was able to do this problem, start to finish? Okay. Yeah, you'll be given that. Hey, Tim just asked the following. Everyone look. He said, will I get this equation? Yes. On the test, you'll have to solve for Kp from Kc, but you'll also have to go from Kc to Kp. You'll only get one version. It's just math. Kp equals that divided by that. Don't feel like it? It's Tim giving me attitude. Yeah. Okay. Problem number 2. Here we go. Let me see if there's anything dumb in here. NH3. NH3. Would anyone like a hive sticker before I throw them in the garbage? They look good on water bottles. Okay, who else? Oh, okay, didn't make it that far. I'm sorry. Okay, you work on this problem. I'll work through it as soon as I'm done cleaning my table, which I don't do very often. So the first thing is to write out N2 plus H2 forms NH3. Then what would you have to do? Balance it, put a 2 in front of the 3, put a 3 in front of the 2, and we have a 1 there. 1, 3, 2. Okay, the next thing we would do is put it in here. 1 and 2. 3 H2, 2 NH3. That's what we need to do. I, C, E. Okay, coming back up here, it said, whoops, not 0.2. You had 2 of all of them, right? All right. I'll just wait till you're absolutely silent. I can wait 10 freaking years. I don't even care. All right. At equilibrium, there's 1.7 of nitrogen. Well, that's not too bad. And it's lucky. What makes this lucky that I gave you nitrogen? It's the 1. That's real lucky. So I'm going to put a minus, and a plus. The products go down. These go up. So 0.3. You're right with that. Then this would be 0.9. And this would be 0.6. So I have 1.1 and 2.6. Fair enough. All right. Then my only product was squared. Is that right? Yeah. Then my 1.7, is that the 1 or the 3? Okay. And my 1.1 was cubed. And I heard 3.0-ish. Is that what I heard? 2.9. Okay. 3 sounds good. Okay, now you all wanted the temperature, and that is necessary if you calculate it for Kc instead of Kp. But what made this a Kp problem? That it's in pressure. Okay, so now let's pretend this happens at 400 degrees Celsius. And that is Celsius on purpose. This reaction happens at a really high temperature. If it happened at that temperature, what would Kc be? All right, so we would have to, we know Kc equals K, sorry. We know this, correct? So Kc then would be pretty easy to solve for. It's Kp over RT raised to delta N. Uh, 673, right? And then the change in moles would have been 2 minus 4. Is that right? I'll check. Okay, 2 minus 4. Anyone type that in yet? 9,000 what? 119? Well, 9119 and 9120 are pretty much the same thing to me. Okay. Are we all right that that's a big number? Yeah, doesn't matter. It's a big number. Okay. Thumbs up. Can we do them? Now, a ton of you freaked out. You're like, I don't know what KP is all of a sudden. KP is the same KEQ, just we're using pressures instead of concentration. Fair enough. Okay. This one's from the test, so why don't you try this one now? Oh, it asks for moles. How dare I? This one's tricky. Well, I better tell you now before you screw up. What's different about this than all the rest of them so far? No. 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 All right. It gives you KC. It's at 100 degrees, or sorry, it's 80 at 100 degrees. But be careful, it gives you moles and it gives you a volume. If you have to use concentrations, you have to divide your moles by your volume. This might not matter in the long run on this one. Just do what you think and we'll see how it goes. I'll have to look. Okay, someone remind me to unpause when we do this. Took that long for you guys to remind me. Oh, okay. It's all right. Now that I've done it, this is not on the test. Now that we're working through it. This, by the way, usually ends up having to use the quadratic formula. Not this one. Not this one. Because we were able to square it right there. When it's not, it sucks. All right, I'm going to multiply both sides by 0.64 minus 2x. And that will be what x is equal to. You with me, sort of? Yeah, this is all math. All right, someone tell me what 8.94 times 0.64 is equal to. 5.7 minus someone 8.94 times 2. All right, what would you do now? Why did I even do this problem? No. I need to add 17.89x to both sides. So over here I have 18.89x equals 5.7. Then what? So x is equal to 0.3. Whoo, we ready? So this is really 0.6. Really? 0.3. 0.3. Now, I'm going to just ignore that this happened in 2 liters because I've set you astray here. But I'll talk about it after we do this so it doesn't confuse anyone. So what do we have at the end here? 0.0. Okay, Slate. 0.04. What do we have here? All right, so the question asks, how many moles of Cl2 and Br2 do you have at equilibrium? 0.3 moles. A lot of work to get that, right? What's that? It's 0.3. Yeah. Good luck. Yeah.
It's just one digit though.
Right. That was sad. Okay, now, how would you do KP? This ice table is not for part B. All this was to find A. KP, you just use KC, right? And you do it. But what's the change in moles? Nothing. So what's the answer? 80.
I like that. So the value of KP. You should have that.
Well, I'm not talking to you. That's why you didn't get it. Sorry, I was talking to my watch, not you. How fun was that? Not super fun.
Really fun. A was not.
I enjoyed it. Okay, how this would be different when we did this is we have to divide. I think. Let me think it through. I think I can do all the math right until I just get to the right to here. But sorry, because it was in a 2-liter. I'll tell you what though, they've removed any of this algebra. If you did have to do this, it'll be a 1. So you won't have to stress about that. But they've definitely gotten rid of these because they're usually quadratic formula equations. That one was made easier because you had an x squared and you had a 2 as the coefficient for the only reactant. And these get super hard when you have 2 reactants and 2 products. It becomes basically impossible. You have to use matrices. So this will not be on the test. It was a problem I thought was. Okay, where are we at? 37? All right. We're going to talk about one tiny thing, and then we'll have just a few minutes to just chill, if you're okay with that. We don't have enough time for a GIM kit. I will give you a GIM kit tomorrow. How about that? We'll go fishing. Sweet, Tim. All right.
Because you need it.
All right. Remember when someone said KQ and I said there isn't a KQ?
Yeah.
There isn't, but there's a Q.
Why? Thanks.
It's not hard. Please. There we go. K and Q are the same math. Everyone chill. K and Q are the same math. Stick with me. K is at equilibrium. I hate writing equilibrium, so I just scribble. Q is at given conditions. Just stick with me for a minute and I'll explain it. But in a nutshell, you will do the same math for K and Q. When you write the expression and you plug the stuff in, it's exactly the same. Q is what helps me know which direction the reaction will go to reach equilibrium. It says, hey, we are at this specific point in time, and these are my concentrations. Plug them in, and that's Q. And then it will say something like the Kc is this value. And if it's not the same, chemistry has to go either forward or reverse. If it is the same, we're going to say it's at equilibrium. Okay, now let's go back to the notes, but ultimately, same math. K is always at equilibrium. Q is called the reaction quotient, and it's where we are currently at those conditions. Okay, to calculate Q, one substitutes the initial concentrations or the given concentrations of reactants and products into the equilibrium expression. K gives the same ratio the equilibrium expression gives, but for a system that is not at equilibrium. Now we got to be careful. It could be at equilibrium. We just don't know if it is. Like we will know K, we'll know these conditions, we plug them in and see, hey, are we at equilibrium? If not, where's it going to go? Okay, who's with me so far? It's the same exact math. All right. If K equals Q, so you do all this math and you get the same answer that K is supposed to be in the problem, Like if I gave you conditions before and you found that Q was equal to 80, and you're like, wait, K was equal to 80. Well, then great. It is at equilibrium. Okay, if K and Q are equal, it is at equilibrium. Next problem. If K, let me get rid of all this writing. Well, that's fine. Let me get rid of this arrow right here. If K is less than Q, then there's too much product and the equilibrium shifts to the left towards reactants. Now, this is drawn this way for a reason. If you'll do this, you'll get these easy get them right every time. I'll come back to this page in a second. But if you just always write them in alphabetical order where K comes before Q, your greater than or less than sign will point the direction the reaction would go. If K is greater than Q, the reaction goes left. If K, sorry, that was less than. Did I say greater than? Whatever. Okay, you know what I meant. Sorry. So now this time, if K is greater than Q, then the reaction is going to go that direction. That arrow is pointing. So put them in alphabetical order, and then your greater than or less than sign will point which direction they go. Fair enough? Okay, coming back if you're writing them down. So when K is less than Q, it means there's too much product. It means the denominator is too big. Sorry, numerator is too big. Product's still on top. So I have to shift towards reactants to bring it down. Good. If Q is greater than, there's too much reactant and the equilibrium shifts to the right. We feel all right about this concept so far? Okay. Do you want to do a practice problem right now or start the day tomorrow with it? Before we do again, kid. You're sleeping.
I'm going to be gone tomorrow, so I want to do it then.
Let's vote. Do it now. Raise your hands. Do it tomorrow. Raise your hand. All right. Well, we're done. Yep.